let us start with the VHDL. Yesterday was the one trial session and we have covered one topic about VHDL. But for the better result, I'm going to start it again. Introduction to the VHDL. Now, VHDL programming is basically came from the Ministry of Defense. Now, VHDL, the word VHDL is actually VHSI, Hardware Description Language. What do you mean by hardware description language? In a common programming language, we have C++, C, Java, and others. These are not run on hardware. They run on the ground kernels. The hardware description language is something different, which includes the description of the hardware, and it can use to model a digital system at many level of the abstraction, ranging from the algorithmic level to the gate level. Now, what history says, why is the requirement of the VHDL? Requirement arises in 1981 under the VHSI programs. In this program, a number of US companies were involved in designing VHSI chips for the Department of Defense. Now, VHSI means Very High Speed Integrated Circuit. VHSI means Very High Speed Integrated Circuit. As you can see. Now, again, we will go further. And in this chapter, we will cover the terms used in this hardware description language. The terms are like entity, architecture, configuration, package, drivers, and others. Now, what is the main concept of entity? Now, entity is the main part of the building this description language. Now, entity describe the external view. For example, what are the inputs signals, what are the output signals, and what are the things that external world is going to communicate with our module. Architecture. Architecture body contain the internal description of entity. A single entity can have multiple architecture, but one architecture might behavioral while another is structural. We can change the architecture. There are three different types of architecture, but every entity should have one architecture. Now, config. Now, configuration is the statement that used to bind the component instant to the entity architecture. Config can be considered to be a part of the list of design. Now, next is the package. Package is a collection of the commonly used data type, subprogram, used in the designing. Think about the package as a toolbox containing the all building designs and every encapsulation of set of related sub programs and everything which has been available. A driver, this is the source on the signal. Now, if the signal driven by two sources, then when both sources are active, signal will be have two drivers. Next, we have a bus. The bus term, as before, we have a concept of bus term as the number of lines or number of groups of signals. In a VHDL, a bus is a special kind of signal that may have its driver turn off. Attribute. An attribute is data that is attached to the VHDL object or predefined data about the VHDL object. For example, current drivers, capability of buffering, or maximum operating temperature of device. These are predefined and it is attached to that object which we are going to generate or which we are thinking or we are designing for someone else. So we have to show that our chip will work on say different temperature, on a different current driver modes and different buffering modes. Generic. Now generic is the VHDL term for the parameter that pass the information to the entity. If the entity is a gate level type, what is the rise and fall delay of that gate? And these are what we call as a generic. Main thing is the process. Now process is the basic unit of execution. In C++, when we write void main, and we start with the parenthesis and end on the parenthesis. In between that parenthesis, whatever we are writing is the main execution part of C++. A similar way in VHDL, there is a process. All the operations that perform in simulation of the VHDL descriptions are broken into small or similar multiple of process, and this process is written in form of that. Describing hardware in VHDL. That is the main motive of this language. Describing hardware in the form of the programming language. Now it has two parts. Consists of two parts. Primary designing and secondary design. Now primary designing units are entity and package. Secondaries are architecture, package body and other things. The secondary design always connected to the primary. There is a library also. The library are the collection of the primary secondary design units, predefined sets, which are available to be used in future for other purposes or for other entities. Now we will elaborate what is entity and how it play a important vital role in VHDL programming. Now, entity. The VHDL entity is specified by the name of entity. You can have to give the name to the entity. So look at the following entity program. Now, entity of mux is like a keyword start with the entity, and in this book, every keyword is returned in the capital letter. And whatever we are writing or giving the name to particular gate or something is written in a small words. Now, entity start with the keyword entity that shows that it started. Okay, and then, for example, we have given the name as a mux, and then we have described the ports which are we going to use. For example, A, B, C, D, and these are all input bits. We are going to use this bit to give the signal to our entity. Now, this is the input ports describing the inputs to the entity, to our module. Therefore, we have written in, and since it's a single bit description, we have written bit. That means A, B, C, D. These are bit type inputs. Now this is the program for 4 to 1 mux. Therefore, we need two select lines. And there is a select line S0 and S1. Now S0 and S1 is a select line for our knowledge. But to our module, it will work like an input given by the user. And they also are bit type. That means a single bit will work. There is no need of buses. We are expecting an output. X is the defined as an output pin for our entity. And the entity ends with the keyword ends and with the name. Now you can see entities start with name of entity and the name given to that entity. For example, here is a mux. And ends with the end keyword and the name of that entity to show that this entity is completely over. Next is the architecture. Now, architecture are of the three types. Structural style modeling architecture, data flow style modeling architecture, behavioral style modeling architecture. And some architecture do have the combination of three. That means the mixed style. Now, this whatever is shown written right now on the screen is a behavioral type architecture. The behavioral type of architecture specify the behavior of entity as a set of statements that are executed sequentially in a specific order. Now, you can see the architecture also start with the keyword architecture that describes that started with the keyword. Now, architecture also related to some entity. It should has to be related to some entity. Okay. Now, this architecture data flow of mux is related to the entity mux. Now, here what it written architecture, whatever the name we have given to the architecture, for example, data flow, and it is connected to the entity mux. Therefore, return off to connect these architecture, data flow architecture by the name of data flow architecture to our beforehand defined entity mux. This is the entity what we have learned before. Now, to connect this architecture with this entity, what we have written of mux. Now, is signal. Now, this signal is the local variable right now. Now, signals is the select the integer. Now, which type of integer? It may be 0, 1, 2 or 3. Okay. So, we have selected select as a signal and we have defined its integer type. Then the architecture begins with begin. So we have given architecture description and then it begin. Now what says the signal? Signal is what? Signal is by the name of select. We have defined signal as a select. Now every signal has been returned with the symbol greater than or equal to. Now greater than and equal to shows that the left hand side is the signal and the right hand side are the conditions that has to be followed. For example, over here, select is 0 only when S0 is 0 and operation AND S1 is 0. That means when our signal S0 and S1s are 0, 0, then the select is 0. And what is S0 and S1? We already defined in entity. These are the input bit. These are the input bit. That means we are giving input signal at S0 and S1. And according to the local variable signal, that is select, will decide the integer value. That means if S0 and S1 both are 0, this AND operation is a logical AND. When both are 0, that give select to an integer value as a 0. Similar way, if S0 is 1 and S1 is 0, these give select signal as a 1 value in the form of data type integer. Next again, when S0 is 0, S1 is 1, the integer value given to the select is 2. Or else, as you see, every sentence ends with the else. Okay? That means whether this is true or else you have to check for this condition or else you have to check for this condition. If three conditions false, that means they are not true. Then the final else shows what will be the value for the select. Now, if three conditions get false, then 3 is the integer given to the select. Now, after selecting one of these integer, our main output x. Now, x is what we have defined as an output bit in integer, in entity. Now, again, we are giving the signal out. Therefore, x is written on the left. Similar way, greater than equal to, and then start. A, A, our input bit. A, our input bit, port. Now, A, x equal to A after zero point 0.5 nanosecond when select is 0. Else for checking the next possibilities. X equal to B after zero point 0.5 nanosecond when select is 1. Else x equal to C after zero point 0.5 nanosecond when select equal to 2. Else D after 5 nanosecond. That means what it says, whether it will be A if select is 0 it will be B. If select is 1, it will be C. If select is 2. And if 3 of these selects are not present, then defaultly it will be D. Okay, the architecture begin with the data flow, name for the entity marks is now ended with the keyword end and the name of the architecture, that is data flow. Now you can see one new thing is that every sentence is written as after zero point 0.5 nanosecond, and this is what we are giving the delay at the output. That means every output X will have its value after zero point 0.9 nanoseconds. Okay? If the select line is 0, if select line is 1, or if select line is 2. Now we will go further. Now what is the co-current signal assignment? Now you can see in the architecture we have given co-current signal assignment, and this is what the architecture we are following in above. Now this select 0, 1, 2, 3 is the behavior of architecture. Now you can see in a typical programming we have C++, C, assignment is executed one after another. Same in VHDL, assignment occurs only when there is a signal. Otherwise, it will not going to execute. Okay. Now select in whatever we like in select. Now since the signal select will have get numerical value assigned to it based on the value of S0 and S1. And this para shows that the symbol greater than equal to is used to signal assignment to the local variable select. Okay, so these return lines are called co-current signal assignment lines. Now signal is what? Select, and assignment is what? 0, 1, 2, 3. And co-currents means this what we have written in when or else. Now event scheduling. The assignment to the signal X, you can see that the select is given a different value, and according to that select, the X is given the value or assignment. Now, assignment to the signal S does not depend instantly. That means each value of signal X contained after the clause, as we have discussed, and giving the delay of 0.5 nanosecond in future containing the new values for signal X. Statement of concurrencies. The first assignment is only the statement to execute when event occur on the port 0, S0 or S1. Second signal assignment, that is about the X. Second signal assignment does not execute unless the event on the signal select occurs. That means second X will not assign any value of A, B, C, D until and unless the select has been assigned some integer value. And this is called statement concurrencies. The two signals assignments in architecture behave from the behavioral model or the architecture of the mux entity. Now, next is the structural designing. This is what we have, a behavioral model. Second is the type of architecture is called structural designing. Okay. Now, this is given as a description for the entity mux which we have learned beforehand. Mux entity architecture in the form of in the style of structural designing. Now here you can see that architecture start again with the keyword architecture. It named by netlist for the entity mux. Now you can see the mux entity have second type of architecture. Okay, and the designing of architecture is different. The first type was the behavioral and the second type is the structural design. Now you can see this behavioral has a different way of writing, whereas the structural has a different way of writing. This is the behavioral architecture for the mux, and this is the structural design for the mux. Programmer can use any of the type for writing its program, depend upon the way or how it behave we can do. Now, in the structural designing, it describes a set of interconnected components. Now there is a component value. For example, component AND gate, which AND the component again, component invert, again it has to be and the component OR gate, again it has to be invert. And the total body of the architecture is divided in two parts, descriptive parts and the statement part. Okay. And what is the descriptive part? All the part that is written before the begin is called descriptive part. And all the statement written after the begin, that is U, U1, U2, U3, U5, U7 is called statement part. Again, there is a local variable and that local variable is signal as 0 inverse. Okay, and these are the local variable. Again, we have to start for the AND gate component. What are the inputs we are going to use? We are going to use port A, B, C as an input bit, C as an output bit. Every component is start with the keyword component and the name of the component AND gate, and it ends with the AND component's word. The similar way you can say invert. Invert has input as a IN1 input bit, X as a output bit. Then again have a component OR gate, A, B, C, D as an input bit, X is a output bit. Now signal, which is the local variable for us to use between begin and end. It is in the between of the box of entity. It's not going to interact with the external world. Okay. Now we have S0 inverse, S1 inverse, X1, X2, X3, X4. All are of the bit type. This completes the descriptive part of the architecture. After the begin, we have U1 statement inverted. Inverted, word inverted comes यहाँ से, ठीक है ना? We are going to use the component of inverted, okay? S0, S1, that means the signal which we have defined in the entity was S0. Now what it does, it inverts the input S0 of the main entity into the inverted form in a reverse, one's complement. Same way S1 also done. Then AND gate says that AND gate A, that is our input A, you can see that input port A with S0, whatever the result of S0 from the inverted, and S1 and the X1. Now this X1 is the signal, local variable signal, as you can see, it's X1. Same way U4 you find in a similar manner. U5 and U6, that means 0 0 1 0 0 1, which is our table, and 1 1. Okay, now U7 is the main gate. Now what it says, U7 is the OR gate, okay, of what? X2 equal to B. We have defined X2, X1, X3 equal to B, X1 equal to A, X4 equal to D, X3 equal to C, and X equal to X. Now what is X equal to X? We will explain it in a further. Now Now you can notice the component U statement U7. Now this 7 statement has a notification as we described above. Now these statements use name associated to match the port signal. Now for example, for instance, port X2 of the OR gate is connected to port B of entity with the first association clause. A similar way, you can say X2 is connected to the B. Okay. Similar way, the last is X is connected to the X. The last installation clause connect the port X of the OR gate component, which is inside the entity, to the port X of the entity. That means this X, which is outside, which is actually the out bit of our program description language. Okay, so this is the type of the structural design of the architecture. Next, sequential behavior. Now, sequential behavior is very similar. Okay, now what it says, for example, this statement architecture says architecture sequential. Again, the architecture start with the architecture and named as a sequential of the entity mux. Right now, we have connected 3 different architecture to a single entity mux. Now what it has? A, B, C, D, S0, S1, which already we have defined into the entity as an input bit. Now local variable select, which is the integer type data type. Now begin. As you remember, in C++ we have used if and else loop. That is only we are going to use over here. If S0 is 0, S1 is 0, then select cell is having the integer type 0. Okay, and this time we have assigned the value 0 by using 2 dot and equal to. The symbol has changed over here, as you can see. If and else loop has been used, nested if and else has been used over here, and the final else select is 3. And the if. Now again we start what is the value of cell. According to what value we got on the cell, the case has been decided. Case is case keyword cell is. When cell is 0, x equal to a. That means output will have input a. When cell is 1, x equal to b. The output bit x will assign the input bit b. When cell equal to 2, x equal to c. If these three are not working, otherwise when others equal, x equal to b. Symbol is in reverse. You can see equal to less than. And the case and the process and the sequence. You can see that the process has been started from here, begin, and it end on the end process. Okay. Now this is called statement, process statement. Now, it start at the line beginning with the keyword process and end the line with the end process. And in between what we have written is the process statement. Now process and the process description. Now statement part of process start at the begin word, and end at the end process line. And all statements enclosed by the process are sequential statement. This means that any statement enclosed by the process are executed one after other in a sequential order, just like a typical programming model or languages. Process execution. As we have explained, if one statement falls, it will check for another. If other statement falls, it will check next value. And according to what value we give the assessment, assign the value for cell. Now, which type of architecture should we follow? So, it's completely depend upon the user, programmer, the way he wanted to write. Now, configuration statement. Configuration, as we have said, an entity can have one or more architecture. But how does a modeler choose the architecture? Okay. Configuration statement is a map component to the entity. With this powerful statement, modeler can choose which architecture are used to model the entity at every level in design. For example, it has return example for configuration. Config mux con. Now, word config is a keyword to start the configuration statement, and the mux config is the name given to that configuration for our entity mux, which we have defined mux, entity mux. And then we have written the statement for configuration. Okay. Now, the proceeding configuration statement read as Now, use the architecture analyst, which we have already defined before, architecture analyst, as an architecture for the topmost entity, which is mux. Now, for the two component instance, U1 and U2 of type inverter are in the analyst architecture. Use entity my inner. My inner. Mhm. Sorry, huh. The architecture version 1 for the library called work. The component instantly U3 to U6. That means U3, U4, U5, U6. Okay, is the AND gate. Use entity my AND gate architecture version 1 from the library work. And U7, which is the main of the type of OR gate, use the entity my OR from the version 1 of the library work. Okay, so we have used endless architecture with our library work. Okay. Now, by compiling the entity architecture and configuration specific earlier, you can create a stimulatable model. But what if you wanted to stimulate a gate? Now, that is, we wanted to use the behave instead of that structural architecture. Now, config mux2, muxcon2 of mux is for data flow and for and the mux2. This configuration named as a muxcon2 for the entity mux. It used the architecture data flow which we already discussed before. Thus data flow for the topmost entity, which is nothing but mux. By compiling this configuration, architecture data flow is selected for the entity mux in the simulation. Now, configuration is not necessary in the standard of VHDL, but gives designer to freedom to specify exactly which architecture will be used for the entity. Default architecture used for entity is the last one compiled into the working library. With this, the chapter 1 of VHDLs ends. And what we have learned in this chapter is the type of architectures, configuration statement, what is entity, what are the different terms, how the signals works, and all. We will look for the next chapter in the next lecture.